Time for us to make our trig teachers proud. We're going to take all those wonderful trig identities that we learned over the years, well, maybe not all of them, but several of them, and practice in how we can use them to solve integration problems. Really, the art comes down to saying, how can we rewrite this into something that's a little bit more easy to manage? So, how do you do it? Well, the answer is practice. Practice. The more you practice, the better you get. And we want to be better. It's an admirable goal. So if you're doing the videos, make use of the pause button. See a problem? Try it out yourself first. And if you do need me, unpause me. But if you don't, that's wonderful. Fantastic. I'm glad you're making progress. So for now, let's begin. Our first problem. Find the integral of sine to the fourth theta cosine cubed theta. So integrals involving sines and cosines are bread and butter. So what can we do? Well, one of the terms has an odd power, the cosine. And when we have one of them which has an odd power, we're like, woohoo! We can do stuff. So what do? Well, the answer is we take whichever one has an odd part and pull one off to the end. So we can say, look, this is really the same as sine to the fourth theta cosine squared theta cosine theta d theta. All right. Now, what are we setting ourselves up for? We're working to get to substitution. The idea is this part on the end is going to act like our du. That's where we're going. That's what we're shooting for. All right. So, what do we need? Well, what we need to do is put everything else in terms of sine. This first part is wonderful. But cosine squared, well, now we say, well, wait a second. Cosine squared is essentially like sine squared because of the Pythagorean identity. So, you can replace this by 1 minus sine squared. So what do we really have? Well, we really have, if we multiply this out, it's the integral of sine to the fourth theta minus sine to the sixth theta times cosine theta d theta. And now we're ready. We're ready to write down our substitution. So we have the following. We're going to let u equal sine. Then du will be cosine. Almost like we planned it that way. Because we planned it that way. So du is cosine theta d theta. And now, beautiful, beautiful. So this becomes integral u to the fourth minus u to the sixth du. So that's 1/5 u to the fifth minus 1/7 u to the 7. And, of course, it's an indefinite integral, so we're not going to forget plus c. And to finish up, well, go back and replace u. So that's 1/5 sine to the fifth theta minus 1/7 sine to the seventh theta plus c. And we're done. We're done. So these are really fun problems in some sense because it's really simple. You say, when one of them is odd, whoosh, off to the side it goes, and life is good. Well, of course, there's always the question, what if that's not true? Well, let's try another problem. So, integral 0 to 2 pi, 64 sine to the fourth x, cosine to the fourth x, dx. They're both even. Well, when they're both even, that means power reduction. Now, what are our power reduction identities? Well, there's really 3 of them. So the ones that we actually call power reductions, cosine squared, 1 plus cosine 2 theta over 2, sine squared, 1 minus cosine 2 theta over 2. And then there's sine times cosine, which is sine of 2 theta over 2. So these are our ways that we can do power reduction. Now you might say, that doesn't feel like a power reduction. Well, it is in a sense, right? Because we have really 2 terms becoming 1 term. That's what power reduction does. It's like, well, we can trade 2 sines for 1 cosine, or 2 cosines for 1 cosine, or a sine and a cosine for a sine. So it's like we're trading, and we're going down to fewer terms. That's good. Because eventually, if we get down to just a very, very small number, we can actually integrate. And that is wonderful. So I really strongly prefer this one first. And the reason I have a very strong preference is because it really, there's no plus or minus. It's just a single term. So let's apply it. What can we do? Well, we can think of it in the following sense. See, this is the same as the integral from 0 to 2 pi of 64. Then I'm going to think of this as sine of x cosine of x to the 4th power dx. So I say, aha, apply, and what do we get? Integral 0 up to 2 pi, 64, and then we're going to get sine 2 theta over 2 to the 4th power dx. Progress. Wonderful progress. Now, 2 to the 4th is 16. There's a 64. Well, that's very convenient. Almost as if someone had planned it that way. Well, yeah, because it was planned that way. So, when we divide, what do we get? Well, this will be 0 up to 2 pi. Now it's going to be 64 divided by 16 is 4. And then we have sine of 2 theta to the 4th power. Now, thinking in terms of power reduction, we say, it's easy for us to work with squares. So I'm going to think of this sine to the 4th as really sine squared. So sort of in anticipation of what's to come. Because sine to the 4th, we still can't integrate it. We've made a lot of progress. Essentially, if you think about it, there's like 8 total sines and cosines when we began. Now we're down to 4. So we've cut in half. Well, that's wonderful. All right, well, now we'll do it again. So what do we get? Well, integral 0 to 2 pi. We're going to have 4. And now sine squared comes 1 minus cosine 2 theta over 2 squared. Except I've made some mistakes here. Aha! Let me correct myself. This is very, very bad. I can't believe I did that. See, I used x here. This should be an x there. Okay, so that's an x there. And now we should have doubled this. So it's not 2 theta. See, it's double what we currently have. So it's actually 4x. Okay, good. Well, it's good to catch them soon. The sooner you catch it, well, the easier it is to recover. Okay, whew. Good. Well, we forge ahead. Keep going. Keep going. Now, the nice thing here is that when we square the 2 in the denominator, that'd be 4, which cancels with that 4. All right. Woohoo! Cancellation. Nice. Good. So, what do we have? Well, we have that this is integral 0 to 2 pi. So the 4 and the 2 squared cancel. So now we got to square that term. So if we square that, that would be 1 minus 2 cosine 4x, and then plus and cosine squared of 4x dx. All right, now we look at this and we say some of these terms we're pretty happy with. So we're happy with the 1 because we know how to integrate 1. Woohoo! And we're happy with cosine 4x because we know how to integrate that. Now with the cosine squared, we're not yet happy, but we have a plan. See, it's cosine squared. So what can we do? More power reduction. Yes, exactly. We can keep going. We keep going as long as we need. All right, well, let's see what would happen. So if we do power reduction, cosine squared of 4x, this part here would become 1 plus cosine, double that, 8x over 2. So we can update. This becomes integral 0 to 2 pi. There's 1, and there's another half. So that would make it 3 halves minus 2 cosine 4x plus 1 half cosine 8x. And there we go. So we've done power reduction several times, and we've gone down. All of these terms now are just a single cosine, or even just a constant, which means we can integrate. Perfect. So, what do we end up with? Well, we end up with 3 halves x from the first term. Here, the integral of cosine is sine, so we're going to have minus sine of 4x, but now we have to think about what goes in front. Well, it's 2. We got to divide by the 4 because of the integration, so 2/4 makes a half. Integral of cosine, again, sine. And now what goes in front? Well, we already have a half, and we need to divide by another 8, so that makes it 1/16. And there we go. Evaluate that from 0 to 2 pi. Well, 3 halves times 2 pi is 3 pi. Okay, nice. And then we have 8 pi. 4 times 2 pi is 8 pi. Sine of 8 pi is 0. It's literally the same as sine of 0. Because if you're talking about 8 pi, it's like you're doing 4 revolutions around. So you get back to where you started. 16 pi, well, that's like if you did 8 revolutions around. And so even though you might be dizzy, after you do 8 revolutions, you're back to where you started. And so 0. Now 0, 0, sine of 0 is 0, sine of 0 is 0. And so our final answer turned out to be something pretty nice. 3 pi. What a lovely answer. A lovely answer. And here we got to use, in essence, all of our power reduction tools. And we were able to do it. It's the relative ease. It's not too bad. Just have to be patient. Very, very patient. Patience pays off. Okay, good. Well, let's continue. Now, suppose you have the following. Find the integral sine cubed y over cosine to the 5th y, dy. Now, we look at this and say, look at the powers. Which one has an odd power? And we say, they both do. And you're right, they both do. So we have 2 choices here. So let's talk about what happens. Let's actually start both our choices, and we'll see where we end up. Okay, so let's do sort of maybe the one that seems the more straightforward one, which is, hey, I see a sine cubed y. Let's pull a sine y out. So we could do the following. We could think of this as the integral of sine squared y over cosine to the 5th y dy. Oh, whoops. Sine of y. I forgot that we pulled that little sine of y to the side. dy. There we go. There we go. Now, our challenge, what do we do about the sine squared? Well, because the goal is that's going to become our du. So the sine squared, we say no problem. we can replace that. That becomes 1 minus cosine squared y over cosine to the 5th y times sine of y dy. Now, at this point, we're ready. We have everything in terms of cosine, and with the exception, there's one sign at the end, and that's going to become our du. So, if we said, hey, let's let u equal cosine y, then du is negative sine y dy. Or we could say minus du is sine y dy. And with that substitution, we would get the integral of 1 minus u squared over u to the 5th times a minus du. Okay, so that's one of our options. Let's talk about a different option. Okay. The other thing that we could do is we can pull off a single cosine. Now you're probably looking at this and saying, how do you pull off a cosine? It's in the denominator. Well, you can do it, and here's how. If you want to pull a cosine off from the denominator, imagine multiplying both top and bottom by cosine. Okay, well, that would be the following. You'd have the integral of sine cubed y over cosine to the 6y times a cosine y dy. Right? Because look, the cosines cancel, so it is exactly the same as before. Now, we say, great, this cosine y dy will act like our du. We just have to figure out how do we handle the denominator. Good question. Well, and why do we have to do it? Well, because we need it in terms of sine. But here's the thing. We say, look, cosine to the 6, this term down here is secretly the same as sine squared, sorry, ahead of myself, cosine squared cubed. And so what we can do is we can say, hey, this is really the same as sine cubed y divided by, and cosine squared, I can replace it, 1 minus sine squared y cubed, and a cosine y dy. All right, wonderful. Now do the substitution. What's the substitution here? Well, the substitution here is u equals sine y, and then du is cosine y. There's no negative sign. Oh, even better, right? Well, maybe. So, what do we end up with? Well, this is going to become the integral of u cubed divided by 1 minus u squared cubed du. And now comes the question. Which integral should we do? Because we're definitely valid in everything we've done so far. So we've taken our trigonometric integral and we said, well, we had two choices and we got down to two integrals which are algebraic. And so the question is, which one is the superior one? And I think we kind of all more or less agree on which one is the one we want to go with. But maybe we can't quite say why. So I want to try to see if I can justify the why a little bit. Because I think if we can actually say it out loud, it helps us to say, all right, good, I understand. So here's the thing. We love addition in certain places. And we don't like addition in other places. And that's really what it boils down to. There's like a good addition and then there's bad addition. So, what's good addition? Good addition is something like here. This is a good addition. Because it's up in our numerator, and good addition says, oh, you can separate things and pull them apart. This is a bad addition because it's in the denominator, and really more precisely, it's sort of inside something. So good addition is when you have the addition happening on the outside of pieces and allows you for separation. Bad addition is when it's on the inside, which means you can't pull things apart. Overcoming, that bad addition is not a very easy thing to do. So we're not going to attempt to do it. And instead we're saying, look, we're going to pick the one where the addition is easier for us to work with. So we're going to go with the good case. Okay. All right. Now you might say, could you do this integral? The answer is yes, if you have the right tools. Now, what are the right tools? Well, that's something we'll be a little bit partial to. We'll get to that in a different session. So let's move on with our problem. Okay, so what do we have? Well, we break this up. Now, because of the minus, let's do that first. This is the same as u squared minus 1 over u to the 5th du. Well, now we break it up because it's good addition, which says you can break it up. I can really break it as u squared over u to the 5th and 1 over u to the 5th. So we'll have, we'll go ahead and do it slowly here, just so no one can accuse us of sleight of hand, of course. Okay, so this is really the integral u to the minus 3, 2 subtract 5, minus u to the minus 5. Okay. Well, perfect. Exactly the kinds of things we want to integrate. The integral of u to the minus 3, well, you'd add 1 to the exponent, would be minus 2. Okay, so u to the minus 2. Divide by negative 2, same as multiplying by negative a half. U to the minus 5, add 1 to the exponent, is u to the minus 4. Divide by negative 4 is the same as multiplying by negative a fourth. There was already negative there, so 2 negatives make it a positive 1/4. And then plus c. Well, we're almost done. The only thing left to do is to say, what was our substitution? And this was the cosine. Okay, so if we'll do one more step. So this is 1 over 4 u to the 4th, and then minus 1 over 2u squared. We could do some various things. We could do things such as say, oh, hey, let's put things together, right? So, for instance, what can we say? We can say common denominator is 4u to the 4th, right? So this would become 1 minus 2u squared over 4u to the 4th plus c. Okay. All this is just playing around. And our final thing to get our answer is we plug it in. U equals cosine. So we have 1 minus 2 cosine squared y divided by 4 cosine to the 4th y, and then, of course, plus c. And there we go. What a lovely answer. A lovely, lovely answer. All right. Now, you could do a little bit more of playing around if you wanted to, but I don't think we should. If you want to sort of trick your friends and make them go like, what? How is that even possible? There is a little fun fact here, which is if you go back to the following, if you go to the double angle identity for cosine, so cosine squared of something, call it theta, well, we often write it as cosine squared theta minus sine squared theta. It turns out that you can do the following. Oops, sorry. That's not cosine squared. That's cosine 2 theta, excuse me. is cosine squared minus sine squared. Well, it turns out you can replace the minus sine squared by 1 minus cosine squared, and you get, this is 2 cosine squared minus 1. And it's almost what you have there. So you could, for instance, say, look, this numerator is actually minus cosine of 2y. So if you really wanted to, you could have written this as minus cosine of 2y divided by 4 cosine to the 4th y plus c. But at this stage, we're just having fun, and really that incredibly obfuscates what we're doing with this problem, and even more so than we need to. So, okay, all right, that's good enough. Good enough. Well, let's keep going. And our next problem will be, something different. So, find the integral of tangent theta times sine cubed theta. Okay, well, what's going to make this interesting? Well, one thing that will make this interesting is that we see it's tangent and sine mixed together. And that can make things a little bit challenging. All right, well, let's see what we can do. So, generally speaking, when you have something involving trigonometric functions which are really not compatible, so sine and cosine go great together, secant and tangent go great together, cosecant and cotangent, if you have somebody who really loves negative signs, well, that's another story. But tangent and sine are not in the same group. So what we do is we want to put them into the same group, and when in doubt, put everything in terms of sine and cosine, just because the sine and cosine are so easy to work with. So, idea number 1. Let's see what we can do by saying, okay, tangent is really the same as sine over cosine. So you have sine over cosine, and then we have a sine cubed. Okay. All right. Well, progress, right? Of sorts. And so we get that this is the following. Integral of sine to the 4th theta over cosine theta d theta. Now, at this point, you're like, aha! If we go through our philosophy, the cosine has an odd power, and so, since cosine has an odd power, what we can do is pull it out and keep going. And so you could, and let's just talk about what would happen. So one option is you could say, oh, this is the same as sine to the 4th theta over cosine squared theta times the cosine theta d theta, which would give us what? Well, it would become sine to the 4th theta over 1 minus sine squared times the cosine theta d theta. And we could keep going. Now, we're not going to go that route. The reason we're not going to go that route is because, in the spirit of what we just talked about a few minutes ago, hopefully you were watching, right? Of course, you're a great student. Of course you'd watch it. A minus in the denominator is nothing to toy with. It actually becomes kind of a little bit challenging. And so we really want to avoid things which have negatives in the denominator, which means we're not going to pursue that option. Well, what can we pursue then? What we can pursue is we can look and say, look, sine to the 4th, what's a way to think about sine to the 4th? Well, one thing we can do is we can think about it in the following sense. Let's pull off a sine squared. So it's sine squared over a cosine. And let's see what we can say. Well, what does that allow us to do? Well, we can say the following. For instance, if we just replace one of our sine squareds by 1 minus cosine squared, Then we have a sine squared over a cosine. Well, that would be what? Well, that becomes the integral of sine squared over cosine. And then, right, sine squared over cosine. And then the other term, cosine squared over cosine, would become minus a sine squared times a cosine. Now, let's think about these two terms. Are either of these two terms happy? In other words, we're like, ooh, we see what to do. I claim the second one is actually pretty good, right? Because what can we do? Well, if we think about what we have here, we have sine to an even power, but cosine to an odd power. And the derivative of sine is cosine. Perfect. Perfect. That's exactly the kind of thing that we need. That is good thinking. But that first term, not so happy with. Not yet. But you know what? We can replace this first term by 1 minus cosine squared again, right? Sure, of course we can. Of course we can. And what happens if we do? Well, we'll get 1 minus cosine squared over cosine, and then that term on the end, minus sine squared times cosine. Okay, well, let's see. What does that become? 1 over cosine is secant. Cosine squared over cosine is cosine. And then this last piece, minus sine squared over cosine, and that is lovely. And so now we have wonderful things to work with. Indeed, we have the type of things that we're excited about. Problems where we can make progress. That's what we want. Problems where we can make progress. And each piece here is something we can integrate. So the integral of secant is what? Natural log secant plus tangent. It's that kind of weird one, but we got to know it. The integral of cosine, well, the integral of cosine is sine, so we have minus sine. Now, what's the last part? Well, the last part, this is the happy part we had before. It's substitution. If you let u equal sine, then you get that du is cosine. So what this last piece becomes is really, it's like we're integrating the minus u squared because of that minus u squared du, which is minus 1/3 u cubed. So we say, great, wonderful. So that says our last thing is going to become minus 1/3 from that minus 1/3. And then we have u cubed is sine cubed. And plus, of course, c, because it's a definite integral. And we're done. Life is good. Life is wonderful. We were able to make it work, which is something we'd like to be able to do. We like it when things work out. It's a lot better than the alternative. And so there we go. Now, you might say, well, what's the takeaway for this one? I think the takeaway for this one is you just sort of have to be patient. Put everything into sine and cosine and look for ways to rewrite your pieces. You don't always have to rewrite everything at once. It's just, okay, rewrite, okay, see what you have. Okay, this part is okay, pull it to the side, rewrite again, and play around with things. Using trig identities, it's not so much that there's this algorithmic procedure. It is kind of almost more like an art where we have to think about, okay, what's the right thing to do now? The mantra for problems, whether it's trig or anything else, is always to say, what can I do to make things easier to work with? Keep things simple. it's the same thing that said, hey, we don't want to go too far down here because we're getting a negative in our denominator. That subtraction downstairs does not make things simpler. It makes things, if anything, more complicated. And so we want to be careful. We want to be the right amount of careful. All right, well, we're done. What a fun problem. What a fun problem. Okay, well, of course, there's always more. Just when you think you've had the last of the fun problems, there's another one coming. Okay. So, find the integral from 0 to pi fourths of the root 1 plus cosine 4x dx. All right. Well, that looks like fun. Let's see. What can we do? Now, there's two approaches to this problem, and let's go ahead and do both, and we should get the same answer, and if we don't, we're going to have to sit here and go like, I wonder what happened. Well, I'm optimistic. I think we'll get the same answer. You see, it shouldn't matter how you do a problem, because the answer is one value. And so it's kind of a fun thing, by the way, this idea in mathematics. It says, I can have two different ways to approach a problem, and therefore the answers must agree. And sometimes you can actually get a lot of information by saying, these two answers, which look very different, I know agree, and that says something about these answers. It says they're connected, and you can do a lot of fun mathematics that way. That's a different story, though. Let's get back to this one. So what are the two approaches? So we'll say method 1 is, let's just call it conjugation, because what we're going to do is we're going to do conjugation. That's why it's a pretty accurate name. And the idea, both the methods have the same philosophy at its core. It says, boy, it would be really great, wonderful, if we could get rid of that square root. Well, let's try to do it. And the nice thing about conjugation is it says, let me make things into squares. So essentially what you end up with is an a squared minus b squared. You're like, that doesn't get rid of square root, Steve, you silly guy. But in trig, there's this wonderful identity that says 1 squared minus cosine squared is a sine squared. And that lets us say, a squared minus b squared in that case does become a perfect square. It's a nice fact about trig. So that's why conjugation can work. So what do you have? Well, this will become integral 0 to pi over 4. And we're going to think about multiplying by the conjugate on the inside. So this is 1 plus cosine 4x over 1, all inside of the square root. We're going to multiply this by 1 minus cosine of 4x over 1 minus cosine of 4x, all inside the square root. And if we do that, what we get out is we get out the following. So upstairs, 1 minus cosine squared of 4x. Downstairs, 1 minus cosine of 4x. And we say, okay, on the numerator, that's the same as sine squared. All right. Downstairs, 1 minus cosine 4x. And now, our moment of truth, getting rid of a square root. Okay. So, this is equal to integral 0 to pi over 4. Square root of sine squared is sine of 4x over the square root 1 minus cosine 4x. Now, I have said a little lie. Let's be careful here. Where's my little lie? It was right at the very end when we said, aha, the square root of sine squared is sine. That was technically a lie. Because what is it? It's actually absolute value of sine. All right. So, are we in trouble? And why not? Well, we have to ask ourselves the question, what's happening to sine of 4x in the range we care about? Well, what do you mean by what we care about? Well, we only care about between 0 and pi over 4. Well, so if you multiply by 4, we only care what's happening to sine between 0 and pi. Now, if you think of the unit circle, between 0 and pi, that's the top part of the unit circle. The sine corresponds to the y values. So if we're on the top side, sine is greater than or equal to 0, which means we don't need the absolute value. Okay, whew. Good, good. So this really is just 0 to the power of 4. I'll rewrite it again. Sine of 4x over the root 1 minus cosine 4x. Now you might say, okay, but what if it had been from, say, 0 to pi over 2? What would we have done? Well, we would have stepped back and said, okay, we have an absolute value, and then what we would do is we would break up our integral into parts and say, all right, here is a part where we're positive, here's a part where we're negative, and then we can treat them separately and then figure out what happens. So that's what happens if you ever have it saying, oops, I'm changing my plus to a minus. Okay, break into parts, break into parts. Now, the way to finish is substitution. Because we say, look, if you put this, just what's inside that square root, because after all, substitution is an inside job. So if u equals 1 minus cosine 4x, then what's the derivative? Well, the derivative of cosine is negative sine. So you actually end up with a positive sine of 4x times by 4. Well, all right, but we can do our fancy, hey, that's really 1/4 du is sine of 4x, and I forgot to write down the dx, but that's all right. Now we have it. And so what do we have? Well, we have the following. After we make that substitution, we say, okay, we're going to integrate, and let's go ahead and do the bounds. When we plug in 0, 1 minus cosine of 0. Cosine of 0 is 1. 1 minus 1 is 0. Plug in pi over 4. 1 minus cosine pi. Cosine of pi is minus 1. So 1 minus minus 1 makes 2. And then we have the sine of 4x dx becomes a 1/4 du. So that's our sine 4x dx, 1/4 du. And this square root of 1 minus cosine 4x in the denominator becomes a u to the minus 1/2. The 1/2 is the square root, the negative because it's in the denominator. And now we're like, perfect, perfect. All right, so what do we end up with? Well, add 1 to the exponent, that'd be u to the 1/2, divide by 1/2, same as multiplying by 2. So we end up with 1/2 u to the positive 1/2. Evaluate from 0 to 2. If you plug in 0, you get 0. Beautiful. And if you plug in 2, we get what? Well, we get square root of 2 over 2. And therefore, that's our answer, square root of 2 over 2. Okay, good. Well, you notice we left ourselves a lot of space because we said we're going to do it twice. This problem is so nice. Let's do it twice. What's the other method? So method 2 is to say what? Well, it really is sort of reverse power reduction. Now, in some sense, if you think about what power reduction says, it says, hey, I want to take something that's a square and make it not a square. So reverse power reduction says, hey, I want to take something that's not a square and make it a square, which is wonderful if you have a square root. So how does this work? Well, if you think about the following, where do you see a 1 plus cosine? You say, oh, if you look at cosine squared of theta, that's 1 plus cosine 2 theta over 2, which tells us that 1 plus a cosine 2 theta is really 2 cosine squared of theta. Okay, so applying it here, if you think about the integral 0 to pi over 4, we have a 1 plus cosine of something. In our case, 2 times something is 4x. So we could say, look, that's the same as 2 cosine squared of, and this is the part where we want to make sure we don't make too many mistakes, it's going to be 2x, right? Because 2 theta is 4x, so theta is 2x. Okay. So, well, now we say, great, take our square roots. And what do we get? We get square root of 2 and cosine of 2x and dx, and we're integrating. But now you're like, whoa, wait a second. We have the same issue, right? It's the square root of a square. So technically we think maybe it's an absolute value. How do we check? Well, we think about what's happening. So I have the cosine function, but I'm not looking at cosine everywhere. I'm saying cosine 2x, x goes 0 to the pi over 4. So if I double from 0 to the pi over 4, it's like going 0 to the pi over 2. That's just the first quarter of the circle. So from 0 to pi over 2, I'm in the first quadrant, and my x value, which is the cosine, is positive. So I can just drop the absolute value. I'm safe to do it. Okay, so this is the same as integral 0 to the pi over 4 of root 2 and simply cosine 2x. And now we're most of the way done, right? Well, why? What's the integral of cosine? The integral of cosine is sine. So we get a root 2 sine of 2x. And now we say, wait, don't forget, you got to divide by 2. Because you have to account for that 2 on the inside. And we're going to go from 0 to pi over 4. Well, plug in pi over 4. 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1 times root 2 over 2. So you get a root 2 over 2. Ooh, promising. Plug in 0. Sine of 0 is 0. So that goes away. Aha! Exactly the same answer we had before. So that says, look, they're both valid. We both get to the same place. Is one better than the other? Well, I don't know. If you can remember your identities, maybe the reverse power reduction is simpler, but they both work. And the key is, don't think about, oh, I have to have the right way. Remember, do it the way that you understand it. Because if you don't understand what you're doing, it's hopeless. Forget it. Forget it. But if you understand, even if it takes an extra step or two, then you're okay. Because it's like, all right, you know the process. You can make sure you're doing things correctly. All right, well, good. We're making great progress. So we should go on and try something a little different. Find the integral secant cubed t dt. Now, if you watched our overview video of this topic, you might recall, Steve, when you said find the integral of secant cubed, you phrase it as a long journey lies ahead. Because it's secant to an odd power. Yes, and it's time for us to take the journey. Oh, this will be fun. Okay, so, all right, what can we do? It's actually a great question. I mean, what can you do? What can't we do? Well, it's not one of our things we already know the integral of. Otherwise, we wouldn't ask the question. I mean, you can do various things. You can apply something like secant squared is related to tangent squared, but we still get an integral that we didn't know how to integrate. So we're not going to do that yet. there's not really a clear substitution to make here. And sort of, it's not feeling very promising. But if we dig back a bit, we say, we've recently learned about a wonderful technique called integration by parts. And one of the nice things about integration by parts is it said, look, you don't have to integrate the whole thing. If you can integrate part of it, you can make progress. See, that's one way we can think about integration by parts is, hey, just integrate a part and see what happens. So, is there a part of secant cubed which is easy to integrate? In other words, I don't have to integrate all of the secants at once, just some of them. Well, we do know how to integrate a secant, but that's not a really lovely integral, right? It's log secant plus tangent. But we also know how to integrate secant squared, and that, beautiful integral. So we say, aha, we're going to put on our integration by parts hat and say this integral is the same as two pieces. We're going to have secant t and a secant squared t dt. And our idea here is, okay, this part, it's easy to integrate, so we'll make that the thing we integrate. And the good news is, we're so good at differentiation, we can differentiate anything. At least it feels that way sometimes. Okay, so let's see, what would we have? du would be secant times tangent. Okay, that's not so bad. And v, the integral of secant squared, is tangent. Also not so bad. So we're going to have uv. So we're going to get secant of t times tangent of t, okay, minus the integral v du. So that's a secant tangent squared. All right. At least it feels like we're doing something, because we're doing something. Now, if you kind of remember the mantra we said, having a tangent squared is really more or less the same thing as having a secant squared. So this thing is kind of like a secant cubed. At this point, you're like, no, not a secant cubed. That's what we're trying to do. But you should say, oh, a secant cubed, you say. Let's see what happens. Let's see if we can gently massage and coax something out of here. Now, tangent squared, it turns out that tangent squared is the same as secant squared minus 1. It's one of our nice identities that connects tangent squared and secant squared together. So we say, all right, great. So we really have secant t, tangent t, all right, and then minus the integral of secant t times secant squared t minus 1 dt. All right, let's expand. Well, what does that mean? It means distribute here, and then use the fact that integration we can break up over addition and subtraction. So we get, look, this is the same as secant t, tangent of t, minus secant t times secant squared gives us a secant cubed t, and then minus makes a plus, integral of secant t dt. And now we're like, cool, we know how to integrate secant, that's no problem. And we're like, hey, that's what we started with. But not quite. You see, we started with positive integral secant cubed. We now have the negative integral secant cubed. So they're not canceling. What we can do is move things across and combine. So we're going to move our secant cubed across. We say, okay, perfect. So we have a secant cubed already. Another secant cubed makes 2 times the integral of secant cubed t dt is equal to secant tangent, and then integral of secant. Well, that's natural log of secant plus tangent. And then, as always, a plus c. Okay, well, we're almost there. We're off by a factor of 2. But being off by a factor of 2 is a lovely problem because that means divide by 2 and life is good. So we come to the conclusion that the integral of secant cubed of t dt is a half secant t times tangent t plus a half the natural log of secant t plus tangent t, and then, of course, plus c. And you might say, wait, half c or c? Well, c is a constant. And the nice thing about constants is they're like sponges when it comes to constants. Any constant can be absorbed, gets eaten up, gobbled by the constant. Functions can't, but constants can. All right, so that's it. We're done. Well, that wasn't such a bad thing, but maybe not the thing that we would have thought of originally, right? Because we said, oh, integration by parts, do it once and rearrange, and we get our answer. So that's why it can be a little bit subtle. Now, of course, this is secant cubed, so we now can integrate secant and secant cubed. You might say, well, okay, what about higher powers of secant? Can we do something for that? And the answer is yes. So let's really commit. Here we go. So the problem. Find the reduction rule for the integral of secant to the n, t. Now what's a reduction rule? A reduction rule says, look, I want to integrate something, so I'm going to say this thing I want to integrate is really connected to a simpler thing to integrate. So it reduces the complication. So another way to think about it is like, oh, I have a hard problem. Here's a slightly less hard problem. That's what we're after. That's what we're after. So it even says it explicitly. Look, we're going to say an integral of secant to the n. We're going to connect to an integral of secant to a smaller power. All right. And now there's actually a second part to this problem, which says, hey, let's talk about the integral of secant to the 7th. Wow. Okay. So we're really, kicking it up a couple notches. Of course, well, let's see where we end up with. All right. So let's begin. Now, if we did secant cubed, which we did if you're following along in order here, that was the previous problem, you might remember what we said. Said, well, it's not so clear what we can do, but secant squared is not so bad. And we'll think of secant squared as like a part of secant. So, an idea. Here we go. So we're going to say our integral of secant to the n, t dt, is the same as the integral of secant to the power n minus 2 t, times a secant squared t. Got ahead of myself. I was going to put down dt, but we forgot, needed the secant squared. Okay, and now we say, hey, good news. Secant squared, we can work with that. So the secant squared, we say this part here, that's going to become our dv. Secant to the n minus 2, that's our u. Pretty much, we're pretty good at differentiating pretty much anything. Like, okay, you give me something to differentiate, I can do it. And so oftentimes it's which part can we integrate? That's the challenge in integration by parts. And okay, so integral of secant squared would say, okay, that's not so bad. That's tangent. All right, here, well, we've got to be a little bit careful. What's our du? So the n minus 2 comes down. Secant to 1 less power. Okay, so if you take secant to 1 less power, n minus 2 minus 1 would be to the n minus 3. We're doing the chain rule if you're following along. Okay, so power comes down to 1 less power. times the derivative of the inside. Well, so times the derivative of the inside is the secant times the tangent. So, let's clean it up. That's really an n minus 2. And then there's another secant, so that's really a secant to the power n minus 2 and a single tangent. Okay, so there's our du. So what do we have? We have uv. So that is secant to the power n minus 2 times tangent t, uv, minus the integral v du. Well, so that'll be n minus 2. Then there's going to be a secant to the power n minus 2 t, and tangent times tangent makes tangent squared t. And we get back to their philosophy that says, oh, tangent squared is essentially like secant squared because there's a nice connection. And so the nice connection, we say, hey, this piece right here, tangent squared, is really secant squared minus 1. So what do we get? Well, we can say it's the following. Well, we have secant to the n minus 2 t tangent t. Then I'm going to distribute through. So minus, I'll pull out the n minus 2 integral. Secant to the n minus 2 times secant squared would be secant to the n. Okay, and then minus n minus 2 times secant to the n minus 2 times minus 1 makes a plus n minus 2. And we're going to have the integral of secant to the n minus 2. Okay, well, we're almost there. Notice, what are we after? Well, we want to connect the integral of secant to the n with the integral to a secant to a smaller power. There's our integral of secant to a smaller power. What's the last thing for us to do? Well, what we have to do is put those terms together. So, if we put them together, so we add n minus 2 across, and we say, okay, if we add n minus 2 of them plus 1 of them, we're really going to have n minus 1 times the integral of secant to the n t dt is equal to, and then here it's secant to the n minus 2 t tangent t plus n minus 2 times the integral of secant to the n minus 2 t dt. That's what we're going to have. Well, let's do the last thing, which is saying, hey, we want to get rid of this n minus 1. So how do we do it? Well, we divide. And so we can say our final answer is the following. We can say, all right, the integral of secant to the n t dt is 1 over n minus 1 times secant to the n minus 2 t tangent t plus n minus 2 divided by n minus 1 integral secant to the n minus 2 t dt. And that's our power reduction. That's it. Okay, well, we're not done fully with the problem. We've done the power reduction, right, because we said, hey, we started with the integral of secant to the n, and now we just have to do secant to the n minus 2. So we definitely have a way to reduce the power. And so we can always keep knocking the power down by 2, by 2, by 2, by 2, by 2. So the last thing is, let's actually try this rule out. Okay, integral of secant to the 7th. All right, I think I might need some space here. So we're going to give ourselves some space. Let's move that up for a second here and copy down our rule. That's hopefully we'll have enough space. So the integral of secant to the nt dt is 1 over n minus 1 secant to the n minus 2 t tangent t plus n minus 2 over n minus 1 integral secant to the n minus 2 t dt. All right, I'm just copying it down again for reference, and let's see if we can make this work. So we'll start with 7. We have the integral of secant to the 7t dt. So we have n equals 7. So if we put in n equals 7, 1 over 7 minus 1 makes 1 over 6. Then we're going to have secant to the 7 minus 2. So that'll give us secant to the 5th t tangent t. Then we're going to have 7 minus 2, 5. 7 minus 1 is 6. So plus 5, 6 times the integral of secant to the 5th, n minus 2. All right, but we're not done because we don't have the integral. All we've said is, hey, this integral involving secant to the 7th becomes this integral involving secant to the 5th. So we're going to repeat the process. That becomes what? Well, it becomes 1 over 6 secant to the 5th t tangent t. I'm just copying the first part because that's good to go. Plus 5, 6, parenthesis. Now, what do we do with secant to the 5th? Well, we come back up here, but now we plug in n equals 5. Okay, 1 over 5 minus 1, 1 over 4. Then we're going to have secant, and 5 minus 2 makes cubed t, and then tangent t. All right, and then plus 5 minus 2 makes a 3 over 4, and then we're going to have the integral of secant to the 5 minus 2 is secant cube t dt. And let's go ahead and clean that up a little bit. That's 1, 6 secant to the 5th times tangent. 5 over 6 times 1 over 4 makes 5 over 24 secant cubed tangent. If we multiply 5 over 6 times 3 over 4, well, 3 does go into 6, so that's some good news. And it goes in twice, so this really becomes plus 5 over 8 integral of secant cubed t. Okay, great, progress. Well, but we're not done. We said, hey, that's the integral of secant cubed. Well, power reduction. So this is 1, 6 secant to the 5th t tangent t plus 5 over 24 secant cubed t tangent t plus 5 over 8 times, okay, so now we're doing n equals 3. 1 over 3 minus 1 is 1 over 2. Secant to the 3 minus 2 is just secant to the 1 power tangent t. 3 minus 2 over 3 minus 1 is a half. And then we're going to have the integral of secant. Okay, good. Well, now what? Well, we have to simplify this. And we end up with 1 over 6 secant to the 5th t tangent t. Okay, that's the first term. 5 over 24 secant cubed t tangent t. Then we have 5 over 8 times 1 over 2 makes this 5 over 16 secant t tangent t. Then we have 5 over 8 times 1 over 2 is, again, 5 over 16. And integral of secant, we've reduced, and now we can integrate. The integral of secant is natural log secant plus tangent. And of course, don't forget, plus c. It'd be terrible if we got all the way to the end and forgot the plus c, after putting in all that work to be wrong for a single plus c. And there you go. Look at that. So this is, by the way, why we say when you have secant to an odd power, you have a long road ahead of you, because what you have to keep doing is you have to keep knocking that power down by 2, by 2, by 2, by 2, until you get down to just the integral of secant. And then we're like, aha! And that we know how to do. And so there you go. But see, it's always possible. Now we know how to integrate secant to any power, even or odd. What a wonderful, wonderful, fun problem. All right, well, good. Let's switch gears. So, our next problem, find the area inside the polar curve where r equals 2 sine 2 theta, sine of 2 theta. So, the good news is we actually know this problem, the type of problem anyways, automatically. It tells us that there's area and that it's a polar curve. So we're like, wow, fantastic, perfect. We know how to do area and polar curve. We pull out our formula. And remember the basic idea, especially because we're going from the curve all the way back to the origin, we say, what's happening? Well, the area is you go from your starting to your stopping. In this case, you go from angles. The good news is we actually know the angles. It tells us 0 to pi over 2. And 1/2 our radius squared. We usually call it r squared d theta. And the idea here is these are little tiny pi wedges. So that's what's happening. So our radius is this r, which is 2 sine theta, sine of 2 theta. So other than just remembering the formula, it's not too bad. Say, okay, great. Well, so what does this become? For us, it becomes the integral 0 pi over 2, 1/2 times 2 sine theta, sine of 2 theta, squared d theta. Well, 1/2 times 2 squared makes it 2. So we have a 2 integral 0 to pi over 2. And then we have the two terms, sine squared theta, sine squared 2 theta, d theta. Now we have to start thinking, how do we approach this problem? And it's not that there's a wrong way or a right way to approach problems like this. We just start to think about, well, what can we do? Now we're in luck in that these angles are kind of nice. See, right now they're a little bit incompatible. If you think about what we have one of them is theta, and the other one is 2 theta. But they just differ by a multiple of 2. Now, why is that nice? Well, because that says we can connect them together. We just have to figure out, okay, we really want them to be consistent. So when you're working with trigonometric functions, you need to do something to make the insides match up. At least if they're multiplying. If they're adding, forget it, don't need to do anything. But when they're multiplying, like, okay, we need the insides to match up. So there are sort of two ways we could go. One thing is we could say, I could do power reduction on, well, not power reduction, double angle on the sine of 2 theta and put everything in terms of theta. Or I can do power reduction on the sine squared. And if I do that, what will happen is this will become like a cosine of 2 theta. Now between the two, we should go power reduction. The reason I say we should go power reduction is, as much as possible, we want to sort of be coalescing things, merging things together. If we replace sine 2 theta by 2 sine theta cosine theta, we're actually adding stuff. The more we add, the more challenging things become. The more we can take away, the simpler things become. So we're saying, all right, we're going to do the following. This sine squared term is going to become a 1 minus cosine 2 theta over 2. Now, good news for us, we actually have a 2, so we can just do some little cancellation here. And so what do we have? Well, this is the same as integral from 0 to pi over 2. The 2's are gone. Sine squared of 2 theta, and then minus sine squared of 2 theta cosine of 2 theta. Great. Beautiful. Now, the last term we're okay with. Sine squared times cosine. Beautiful. It's perfect. We're ready for a substitution. Life is good. The first term, we're like, hey, power reduction was so nice. Let's do it twice. We can't integrate sine squared, but we can integrate the following. Namely, we can replace sine squared by 1/2 minus 1/2 cosine of double that angle, which would make that 4 theta. And then we have the part on the end. Sine squared of 2 theta cosine 2 theta d theta. All right, well, let's see what we get. What do we get? Good question. Great question, really. And we were going to get the integral of 1/2. That's 1/2 theta. Integral of cosine, well, is sine. So if we don't change the minus, it's still a minus. So it's sine of 4 theta. We need to divide by 4. There already was 1/2, so that makes 1/8. Now here, for sine squared, substitution. U equals sine squared. Sorry, just sine, not sine squared. So if you say u equals sine, then we get that du is what? It's 2 cosine 2 theta d theta. Well, the 2 moves across, so we get 1/2 du is cosine 2 theta d theta. So we really have the integral of u squared at the end, which is u cubed over 3. Times 1/2 makes it minus 1/6 sine cubed of 2 theta. Okay, that was kind of a little bit quick. So if you're trying to follow along, which is good, we want you to, right? What did we do here? Well, after the substitution, it becomes minus u squared du, and then, times 1/2, because we have to account for that 1/2, which is minus 1/6 u cubed. And that's where that came from. Now, we're almost done. The last thing for us is to evaluate. So, great. Evaluate 0 up to pi over 2. When you plug in 0, good news, 0, 0, 0. Perfect. Perfect. What we would like to hear. In fact, the news keeps getting better. Plug in pi over 2, sine of pi is 0, sine of 2 pi is 0. So in fact, the only thing that doesn't go away is this 1/2 times pi over 2, which means we're going to end up with pi over 4. And that's our answer. That's it. Wow. Wow. Amazing. Amazing. And it's actually kind of an interesting answer because there's something else that has an area of pi over 4. Namely, if you take a circle of radius 1 in the first quadrant, which looks something roughly like that, that also has an area of pi over 4. But nice, clean answer. Cool. Well, let's keep going. All right. All right, well, our next problem. Find the length of the polar curve, r equals secant to the 5th of 1/5 theta, where theta goes from 0 to 5 pi over 4. Well, we can see what the problem is, right? It's about length of polar curves. Now, you may not remember that, and that's okay. Our goal right now is not to remember these formulas, and you may not have actually reviewed this one. So I'm just going to tell you what it is. So we have our length of the curve, r equals f of theta, for our alpha less than or equal to theta less than or equal to beta. In other words, that's our range that we're looking over, is given by the following. Namely, we're going to add up from alpha to beta the square root of, and then it's the original function squared plus the derivative of the function squared d theta. It's not too surprising that there's a square root. Indeed, we'd be more surprised if we were doing a length problem and the setup did not involve a square root. So we'll just take this as is. So now that we have our basic formula, we just have to apply it and see where we go. So we have the following. Our length is adding up, well, alpha to beta, 0 to 5 pi over 4, the square root of the original function. All right, so that's secant to the 5th, 1/5 theta squared plus the derivative. Okay, time for us to practice our derivatives, right? Bring the 5 down, and then it'll be secant to the 4th. But of course, that's just our first layer in our onion. So next thing, so we basically took the derivative to the 5th power. Next layer is the secant. Derivative of secant is secant tangent. So we have secant 1/5 theta, tangent of 1/5 theta. And now, if that's not enough, one more layer, the derivative of the inside of that, derivative of 1/5 theta, which is 1/5 squared. Wow! What an expression. What an expression. So now we start to look and say, does it simplify? We hope it should, especially if we've been living a good, clean algebra life. Well, the 5 and the 1/5, that's a simplification. That's good. And so, let's see, what do we have here? Well, we have, let's just focus on this inside part first, actually, before we worry about what it becomes. So we have secant to the 10th of 1/5 theta. That's the first term. Then here, there's a secant to the 4th times another secant, which makes a secant to the 5th squared. Says, aha, another secant to the 10th. Wow, amazing. And then a tangent squared. Okay, and great. Well, we can pull out the secant term, right? Because that's common. And what do we see? We see secant to the 10th of 1/5 theta times 1 plus tangent squared of 1/5 theta. Okay, cool. See, right? Secant to the 10th. That gets the 1, secant to the 10th, tangent squared. Now, 1 plus tangent squared. That's inside the square root, so we'd really not like to have that. Can we simplify? Yes, we can, right? Because we have our identity. 1 plus tangent squared is a secant squared. With that secant to the 10th, we're now up to secant to the 12th of 1/5 theta. So everything inside the square root collapses down in a really, really nice way. As nice as we could possibly hope for. So that's taking the square root of secant to the 12th, which means that's actually a very easy square root to do. So we have 0 to 5 pi over 4 of secant to the 6th of 1/5 theta. All right, good. And now we say, okay, well, how do we integrate something like secant to the 6th? Well, it's a combination of secants and tangents. It's actually just secant. And we say, well, if we see just secants and it's not odd, okay, phew, thank goodness, then what we can do is we can pull off a pair of secants to the end. So we're going to think of it in the following way. 0 to 5 pi over 4 of secant to the fourth 1/5 theta times secant squared of 1/5 theta d theta. With the goal of that secant squared on the end, we're shooting for this to become our du in some sense. We'll have to play around with that. And the way we do that is to say, all that other stuff, this secant to the fourth, we're going to turn that into stuff with tangent, because the derivative of tangent gives us our secant squared on the end. And we go back to the same identity that let us go from there to there. We say, hey, no problem. You see, secant to the fourth is really the same here as saying secant squared squared. So we can think of it in that way. And so if we use this identity that we did here, we say, look, that's the same as 0 to 5 pi over 4 of 1 plus tangent squared to 1/5 theta squared times secant squared of 1/5 theta d theta. Okay. Well, time for us to do our substitution, clean things up, and hopefully it'll become pretty nice. So our inside function, the substitution we're making, is u is tangent 1/5 theta. So the derivative will be what? Well, derivative of tangent, secant squared 1/5 theta d theta. Great, except chain rule says multiply by a 1/5. Well, we'll fix that. What we'll do is move the 1/5 across. So we'll say 5 du is secant squared of 1/5 theta d theta. So let's now update our integral. So what do we have? Well, this will be the integral 1 plus u squared squared. Okay, that's not so bad. We can do that. Secant squared 1/5 theta d theta, well, that's 5 du. So we'll put a 5 du. And now the bounds. Well, figure it out, right? These are theta bounds. Theta equals 0 to theta equals 5 pi over 4. We want to turn them into u bounds. So we plug in 0. Tangent of 0 is 0. Aha! Great! What a lovely bound. When we plug in 5 pi over 4, kind of a weird angle, but that's 1/5 of 5 pi over 4 is simply pi over 4. A beautiful angle, because tangent of pi over 4 is 1. Great. Good. So we're really integrating 0 to 1 of 5 times 1 plus u squared squared du. What a fantastic integral. The kind of integral that we'd be happy to take home, meet our family, and they say, what a great integral you've chosen. So the way we would integrate is expand. So if you expand 1 plus u squared squared, well, you'd have the 1, don't forget, times the 5. Well, let's just put the 5 in front. Okay, so we have 5, then we'd have 1 plus 2u squared plus u to the 4th. And du. All right, well, let's keep going. So if we integrate, it's not so bad. What does that become? 5 times, well, u, and then 2/3 u cubed, and 1/5 u to the 5th, from 0 to 1. Now the nice thing is, you plug in 0, you get 0. So we just have to plug in 1. All right, well, so we get the following as we spiral in towards our answer. So remember, we plugged in 0, we get 0. Plug in 1, we get 5 times 1 plus 2/3 plus 1/5. Everything has, 1 plus 2/3 plus 1/5. The common denominator would be 15. So we can think of it as 15 over 15 plus 10 over 15 plus 3 over 15. Well, if you add up 15 plus 10 plus 3, that gets you to 28. And 5 does go into 15, and that leaves you with 3. And so our answer is 28 thirds. What a great number. I mean, it's not some weird constants. There's no square roots. There's no pi's. It's just 28 thirds. And there you go. Wow, what a problem. What a great problem. All right, well, we keep going. I think we have time for one more. And we're definitely going to need time, because this will be a good one. It's going to really keep us on our toes. Find the volume when the region 0 less than or equal to x less than or equal to pi over 4 and 0 less than or equal to y less than or equal to 3 secant to the 4x is spun around the y-axis. Okay, let's think about what's happening here. So we have our region, and we don't know exactly everything, but we know we're going from 0 to pi over 4. 3 secant to the 4th x, well, it starts at somewhere and goes up. So let's say this is at pi over 4. And so this is our region. Okay, so that's our region that we're going to spin. And now, where are we spinning? Well, we're spinning around the y-axis. So we're spinning this way. Now we have to start thinking, okay, what's the right technique? And indeed, oftentimes it's important to make sure we understand what the right technique is before we get too far, because we don't want to start applying formulas that don't apply. So how do we figure out the right technique? Well, to do that, we have to make a decision. How are we going to integrate? Are we integrating with respect to x or with respect to y? In this case, everything has been phrased in terms of x. X goes from 0 to pi over 4. Y is a function of x. So it makes sense to integrate with respect to x, which means our slices look something like that. When we spin our slices, what we end up forming are these nice little cylinders. So we say, aha, shell method. Okay, good. So what does the shell method say? Well, the formula is the volume is adding up, start to finish. There's a 2 pi, a radius, a height, and a thickness. So these are the pieces that we would go into computing everything. So let's talk about what these things become. Some things are easy to spot, some things are a little bit more subtle. Our volume goes from 0 to pi over 4, right? So that's our A and B. So 0 and pi over 4. That's not so bad. Our radius is that distance from the thin sliver that we're going to spin to, in our case, the y-axis. So in our case, it becomes x. The height is the length up and down. So that's the length from 0 to 3 secant to the 4th x. And our thickness, that's just a little tiny width, and that is what corresponds to dx. Okay, so for us, we say, hey, this becomes integral 0 to pi over 4 of 2 pi, well, actually 2 times 3, let's make that a 6. So we have 6 pi x secant to the 4th x dx. All right, well, what do we see? Well, when we look at this, we're saying there's some trig, there's that secant, and then there's some algebra, there's the x. They're not really that compatible, so we want to do something. And so the easiest thing is when you have a polynomial, it's like, well, let's get that power down. So we want to And so we say, all right, the way we can do that is do parts. And we look at this and say, well, the thing that we should differentiate, well, let's make that the x, because if we differentiate that, life becomes good, 6 pi. We got rid of the x, which means that the part that we're going to integrate, well, secant to the fourth. Okay, well, let's do a little side computation, because I don't have the integral of secant to the fourth memorized, but it's not so bad, right? Okay, so let's do it here on the side. Integral of secant to the fourth x dx. All right, so we're going to work here. And the way we do that is we say, well, look, this is really secant squared times secant squared. All right, and the secant squared is the same as tangent squared plus 1. That's our nice identity that says secant squared equals tangent squared plus 1. Secant squared x dx. And we do the u substitution, and the u substitution is saying that u equal tangent x, then the secant squared x dx is our du. So we say, okay, well, perfect. This becomes the integral of u squared plus 1 du, which is 1/3 u cubed plus u. All right, well, which is, we can squeeze it just, we almost have enough space. 1/3 secant cubed, tangent cubed, because u equals tangent. 1/3 tangent cubed plus tangent. Okay, all right, so there's our side computation. Back to our problem. So, what does v become? Well, the answer is v is the following. It is 1/3 tangent cubed x plus tangent x. Okay, great. So now we carry this out, our integration by parts. We're going to have u times v. So we're going to get 6 pi times x times 1/3 tangent cubed x plus tangent x, and then we're going to go from 0 to pi over 4. And we'll clean that up in just a moment here. Minus the integral of v du. So 1/3 times 6 makes a 2 pi, and then we have 2 pi tangent cubed x, and then we're going to have plus 6 pi tangent x and dx. Okay, so that's v du. So u, v, v du, and it's still a definite integral, so we need to put our bounds. Okay, good, good. We've made great progress on this. Let's go ahead and evaluate, because we can evaluate early if we want to. Notice when you plug in 0, well, you're going to get 0. Nice, clean. And when you plug in pi over 4, well, pi over 4, tangent of pi over 4 is 1. So what you get is this will become 6 pi times pi over 4 times, and here, 1/3 plus 1. Well, what's 1/3 plus 1? Well, it's 4/3. And when we plug in 0, you get 0. And what do you see? The 4's cancel. 3 goes into 6, leaving you with 2 pi squared. All right, great. So 2 pi squared, life is good. Now we come back and say, all right, well, that's lovely for that, but we still got to tackle this part here. So now we've got to integrate tangent cubed, and we've got to integrate tangent of x. Good news is tangent of x will be straightforward. That's actually on our list of things we can integrate. How about tangent cubed? It's not on our list. But it doesn't mean we give up. We've come too far. We say, all right, well, if we can't integrate tangent cubed, can we rewrite it? And of course we know the answer is yes, because it's trig. The answer is always yes when there's trig involved. So it's kind of almost a rhetorical question at this point, right? So we say, okay, look, tangent cubed is what? We can think of it as tangent squared times tangent. And the reason we want tangent squared is that's our key identity. Tangent squared is connected to secant squared. So this is the same as tangent squared is secant squared minus 1 times tangent x. Okay, let's clean up what we have. So from the first term, after we evaluate, because we can go ahead and evaluate now, we got 2 pi squared minus the integral 0 to pi over 4. Okay, now what do we have here? We have a secant squared x times tangent of x times 2 pi. So that'll be 2 pi secant squared x tangent of x. Then we're going to get a minus 2 pi tangent of x. There's a 6 pi tangent of x. So that'll be a plus 4 pi tangent of x. Okay, good. Now, we're almost there. Secant squared x tangent of x. Can we integrate that? Well, yeah, we can. In fact, there's a couple of ways we can do it. And what's an easy way? Well, maybe the easiest way is to say, look, if you let u equal tangent, what's du? The answer is secant squared. Okay, so what does this become? Well, it really, if we think about this whole thing, it's the integral of 2 pi u du. Well, that's easy to do. The integral of that would be pi u squared, which would be pi tangent squared. Perfect. Well, that's great. It's just what we want. We want things we can actually make progress on, right? So, what do we have? We have the 2 pi squared from the beginning. So minus this integral becomes pi tangent squared x from 0 to pi over 4. Then minus 4 pi, and the integral of tangent is log secant. All right, good. Log secant x from 0 up to pi over 4. Well, now let's plug stuff in, and let's see what happens. Plug in 0. Tangent of 0 is 0. Tangent of pi over 4 is 1. So we get 2 pi squared minus pi. Okay. Then here, minus 4 pi. Secant of pi over 4 is square root of 2. If you don't remember it, cosine of pi over 4 is root 2 over 2, also known as 1 over root 2. And then if you flip the cosine, that gives you secant. So 4 pi natural log of square root of 2. When you plug in 0, secant of 0 is 1, log of 1 is 0, gone, gone. And there you go. Now you can actually make it look a little bit nicer. For instance, square root of 2 is 2 to the half. So you can bring the half down. So we could write it as 2 pi squared minus pi minus 2 pi log 2. And there we go. What a problem. It was kind of fun because we said, okay, got to do integration by parts. Got to somehow say, look, got to knock the power of x down, and then we have to integrate secant to the fourth. And in essence, we're like integrating secant to the fourth, and then we're going to integrate that again. So it's like a double integral. Like, wow, that's so cool. But we can do it. We have the tools. We have the technology, and we got an answer. Oh, life is good. What a great way to end our session. I hope you had fun, and I hope you keep coming back, and I'll see you again. Bye.